So the main point of today's lecture is to prove the Hall-Yoshida theorem, but the sufficiency part. So last week we did the necessary part, and today we are dealing with the sufficiency part. So as a quick reminder, let's reread what's the Hall-Yoshida theorem. So the Hall-Yoshida theorem gives a necessary and sufficient condition for a linear operator to be the infinitesimal generator of a C0 semigroup of contractions. So there's a few words that are important here. So of course, semigroup, but C0 and its contractions. Okay, contractions has a meaning that we saw a couple weeks ago. And it's equivalent to the point I and 2I that are written here. So last time we did the necessary part. So if A generates a C0 semigroup of contractions, then I and 2I are verified. And today we are digging into the sufficiency part, meaning that if 1I and 2I are verified, then we are going to prove that in fact A generates a C0 semigroup of contractions. And to do that, let's have a look to see what are the main ideas in the proof, the sufficiency part again. So here, so how the proof works. First, we are going to define what is called the Yoshida approximate of A, and this is defined like that. And then how the proof works. So basically, we are going to prove that A lambda generates a semigroup, and it will generate a uniformly continuous semigroup. And from that, we will see that as lambda goes to infinity, this A lambda converges to A, and so will be a then after we're taking the limit of lambda at infinity, and this will gives us the result. So the proof relies on two lemmas that I'm going to show you right now. The first lemma is you are going to do this computational stuff. So those are results. So you have to do some computations. And so you have three equalities. So this is the first lemma. So you see up here as lambda goes to infinity, you have some results here. Then relying on these results, we are going to prove another lemma, which I show you here. So which says that in fact A lambda generates a uniform continuous semigroup of contractions. And furthermore, you have this equality. And so with all those work, then we are going to prove that in fact, as lambda goes to infinity, this semigroup converges in some sense to a C0 semigroup S, and that's our result. We'll prove that. Okay, so as a whole, the proof requires some work, and so we are going to dig into that. So first of all, so we are dealing with this lemma here. So please try to read it, to try to understand it, and try to prove it. All right, so let's do this computation. First, let us assume first that x belongs not to X, but to the domain of A. All right, so we have to remind us what's the definition of R. And so R is the inverse of lambda identity minus A. So if I apply lambda identity minus A at R lambda A, if I apply that to X, this is X. Okay, so now what that gives us, you know, if you look here with that, I'm going to see the definition of the approximate of Yoshida. Okay, so let's do that. So what I get is lambda R lambda A so lambda R X, and this one I put it here, minus X equals lambda A R lambda A. Okay, then an X. Okay, that's it. That's it if X belongs to G of A and Y. So now if I look at lambda R lambda A X minus X, this is less than lambda. So lambda is a positive number. We assume that lambda is a positive number. Actually, that's not okay. Let's do it again. So we can prove that this commutes. We can prove that this commute. Okay, R and R, they can commute because you can prove that. It's a small exercise. But I could also, instead of taking that, I could also take the multiplication to the left. I could have done R times lambda identity minus A. So whatever. So I know that that's a small computation exercise. You can prove that R equals RA, 1x belongs to G of A. So then I get that. All right. But I know that R lambda A in the operator norm, it's the point 2i, is less than 1 divided by lambda. So I get that this is smaller than A applied to X in norm. Okay. Let me what. All right, so as you can see, there was this, a typo here. There's no lambda here, right? So, so you get that lambda r minus x equals a r lambda x. So when this is done, you take the norm, there's no lambda here, and then you apply 2i and you get that. And now for a fixed x, this goes to 0 as lambda goes to plus infinity. So here we therefore obtain the results for when x is in g of a, because I have here a of x. So the next step is to extend it, because here in 2.2 you have for all x in x. So I let you try. This is just a small exercise because g of a is dense. So it's just a small exercise to prove that, in fact, the result is also true for x in x, not only for x in g of a, but also for x in x. So I let you think about that. So from the previous computations, we know that the results, the 2.2 holds for x in g of a, but we want the results for not only for g of a, but for all x in x. So since g of a is dense in x, let's choose a y in g of a that will be close enough to, this y can be as close as we want of our x. So now let's do that. So maybe do that. So classically, I will introduce here a y. So I start with that. And I introduce the same thing for my y. So if I put a minus, I had to add here. And then I subtract y and plus y minus x. All right, so now I see here, this I know that is going to be 0 when lambda is infinity. So this is converging to 0 when lambda goes to infinity. And for the other ones, so I remind that for the norm of the operator norm of r, lambda a, is less than 1 divided by lambda. So if I look at this one, is less than 2, so sorry. This one will be less than x minus y. Because the norm of the operator r is less than 1 divided by lambda. Okay, so if I look at this term, I will get here 2. And then this one, I can put it as small as I want, as soon as lambda is large enough. So now, fix any epsilon positive number, and choose, for example, norm of x minus y to be less than epsilon divided by 4. So this will be less than epsilon divided by 2. And you can choose lambda such that this quantity is less divided by epsilon 2. So there exists lambda 0 such that for lambda superior greater than lambda node, our quantity is less than epsilon. So which proves that the result is true for any x in X. Okay, so let's do this another computation. So you write that lambda square r lambda a. Okay, I write in the operator form minus lambda identity. That's here, right? But I write it in the operator form. And then what I'm going to do is just I put lambda in front here. So it remains lambda r lambda a. And then here, I write it, so minus lambda identity minus a times r lambda a. So this is identity, of course. Okay, so I have the equality. And now I put the r lambda a at the end, so I get lambda times lambda identity minus lambda identity plus a r lambda a. So I get lambda a r lambda a, which is a lambda. All right, so finally we need to prove this equality, which says that for all x in GA, a lambda x converges to a of x. So first, by definition of a lambda x, we have that. So for all x in GA, we have that a lambda x equals lambda a r lambda a x. So I told you before, a and r lambda a commute. You can prove that. Okay, it's a small exercise. So this is equal to r lambda a ax. That's why I need that x belong to g of a. All right. All right, but now I know that lambda r for any y in the space X converges to y. That's the first thing that we proved. So this converges when lambda goes to infinity to this thing. That's our first results of today. So as lambda goes to infinity, this converges to a of x. And our lemma is now proved. Okay, so our next lemma says that A lambda generates a uniform continuous semigroup that we call exponential T A lambda. And this is a semigroup of contractions. So the norm of exponential T A lambda is less than 1. Furthermore, you have also the equality 2.5. All right, so try to prove first that A lambda is the infinitesimal generator of a uniform continuous semigroup. Okay, so in order to prove that A lambda is the generator of a uniformly continuous semigroup, it is sufficient to prove that, in fact, the linear operator A lambda is bounded. Okay, this is a theorem. If A lambda is bounded, is a bounded linear operator, then it generates a uniformly continuous semigroup. Okay, that's our first theorem. Okay, so let's do that. So we are going to use that A lambda is so that's our second equality is equal to lambda square r lambda A minus lambda identity. So for hx in x, A lambda x equals. All right, and this is not bad. Why? Now, if I take the norm, this is less than lambda square r lambda A x plus lambda x. But so this is less than lambda square r lambda A norm of x plus lambda x. And this is less than 2 lambda x because this is less than 1 divided by lambda. So we get that A lambda is yes, so therefore A lambda is a bounded linear operator in X. So it generates a uniformly semigroup, uniformly continuous semigroup. So next, so we call it exponential T A lambda, and next we need to prove that the norm of exponential T lambda is less than 1, meaning that A lambda generates a uniformly continuous semigroup of contractions. Okay, so try to do that. So next, we need to prove that this inequality here holds, to prove that, in fact, the semigroup is a semigroup of contractions. So to do that, we again use the fact that A lambda is equal to so it's equality 2.3 in our in the notes, and so we have that this is equal to the norm of exponential t, and A lambda is equal to lambda square r lambda A minus lambda identity. So, but I put the t here, and I get minus lambda t identity. Okay. All right. Next, this is a semigroup. So if you look back to the definition of the semigroup, we construct it as an exponential with an infinited sum. And here I have the identity. So I can separate those. So this is equal to exponential t lambda square r lambda A applied to exponential minus lambda t identity. Yeah, we can prove that because of the definition is constructed with a infinited sum, and yeah, we can prove that. And so therefore now I apply that in norm, I get that exponential t A lambda is less than exponential t lambda square, the norm of r lambda A. Oh, I forgot a step. Let's write it. Let's write this step. So minus lambda t identity. Okay, and this is less than, so for again, sorry, then I write exactly the same. So norm times norm. All right, now this is classical, so is less than t lambda square norm of r lambda A. And here, if you look at the definition of this operator, since you have identity, you get exactly that the norm. You can prove that this is less than exponential minus lambda t. And so finally, I continue and I get here. So now this norm is less than 1 divided by lambda. So I get exponential t lambda times exponential minus lambda t. And this is equal to 1. Yeah. So we prove that actually exponential t a lambda is now a uniformly continuous semigroup of contractions. So what we have done so far, so we have proved that exponential ta lambda is generated by a lambda, and it's a uniform continuous semigroup of contractions. The next step is to prove equality 2.5, which is a simple computation with a little trick at the beginning, just to put a right expression. And why this 2.5 is important? Because it says that, in fact, for t and x fixed, this is a Cauchy sequence with respect to lambda. And so we can take the limit, and this limit, when lambda goes to infinity, will provide us our C0 semigroup. So this is the program of the next lecture.